Okay, this is going to be a video on categorizing triangles. It's the first of our current chapter on triangles. So first we're just going to talk about categorizing triangles with regards to their side lengths and then with regards to their angle measures. Alright, so the first for our categories would be an equilateral triangle. This is a triangle where all three sides are the exact same length. Equilateral. So a picture would be some sort of triangle where all three sides were the same length. So something like that. Now that's a little bit different from something that's equiangular, because that would be all the angles are the same. But this one, equilateral, all the sides are the same. An isosceles triangle is at least two sides are the same. So maybe we have something like this, where we have two of the sides the same and possibly one's different. Like we said, at least two sides are the same. So an equilateral triangle would also have isosceles characteristics because it does have two sides that are the same. But an isosceles triangle, at least two sides are the same. And then a scalene triangle is a triangle where no sides are the same. So, we could have something like this where all the sides have a different side length. Alright, now that's with regards to side lengths. Those are the three categories there. When it comes to angle measurements, an equiangular triangle is a triangle where all three angles are the same thing. So, again, the angles of a triangle, which you may know, we'll talk about again in this section, all the angles have to add up to 180 degrees. So if they're all the same, 180 divided by 3 is 60. So all three angles are the same. Now notice how an equilateral and equiangular triangle look very similar. That's because one is the other. So if it's equilateral, it's equiangular. If it's equiangular, it's automatically equilateral. That is the only polygon that's like that. Rectangles aren't like that. Other shapes are not like that.
Please report to the main office. Desmond Watson, please report to the main office.
An acute triangle is made up of three acute angles. So it still needs to add up to 180, but all angles have to be acute. So we could have something like an 80-degree angle, a 70-degree angle, and a 30-degree angle, where again their sum adds up to 180, but no angle is greater than 90 degrees. A right triangle is a triangle that has one 90-degree angle. Now, I think your gut instinct might say, well, why doesn't it have three? Well, 3 times 90 would be 270 degrees. That's way too much for the angles of a triangle to add up to. So when we look at two right angles, that would be 180 right there and no room for a third angle. So we're limited to one right angle and the other two have to be acute angles. So we can have something like a 40-degree angle here and a 50-degree angle here, something like that. And then an obtuse triangle has one obtuse angle. So a triangle, something like this, where I do have one angle that is greater than greater than 90 degrees, and the other two are smaller. And by smaller, I mean acute. Please go ahead and try out the identification A through H on your own. Okay, we've talked a little bit about the triangle angle sum theorem, where the sum of the angles have to add up to 180 degrees. We're going to do a quick proof to guarantee that for you. So, given information, this right here is a triangle, so we'll say that that's triangle XYZ, and we'll point out that YA is parallel to XZ, which again is given information. And when you have parallel lines, that means I can use those angle relationships that might be between these two parallel lines here. Again, XYZ is a triangle. So if you notice right here, angle 4, 1, and 5, they all should add up to 180 degrees. But 4 and 2 have an angle relationship due to the fact that these lines are parallel. They're alternate interior angles. So angle 4 is congruent to angle 2. And again, that would be the alternate interior angle theorem. if if lines are parallel and cut by a transversal, then alternate interior angles are congruent. And you have the same thing happen on this side with 5 and 3. So I'm going to actually include those on the same step since it's the same reason. Alright, so now I know that angle 4 and angle 2 are congruent, angle 5 and angle 3 are congruent. Well, we talked about how 4, 1, and 5 should add up to 180. Now 4 and 2, 5 and 3 should, they're the same, so I can replace those. So I'm actually going to end up splitting this into 2 steps. So let's do this real quick. Step 3 would be that angle 1 plus angle 2 plus angle 4 equal 180 degrees. Then our reasoning would be 3 angles form a line. And then our last step will be angle 1 plus angle 2 plus angle 3. I'm sorry. This up here should be angle 5. Angle 2 equals 180, and that's going to be because of, and that'll be step 4. And that would be because of substitution. Since we established earlier that angle 4 and angle 2 are the same, I could just take out this 4 and put 2 in its place. And angle 5 and angle 3 are the same. I could take out this 5 and put 3 in its place. These all should add up to 180 degrees. So we've just proved the triangle angle sum theorem. If you real quick would take a look at these next few examples, we could find the missing angle by keeping this idea of 180 in our head. So right now, maybe you don't even write out this step, but in your head you should at least be seeing this equation that 85 plus 35 plus some missing angle measure add up to 180 degrees. So now all we're going to do is figure out what the sum of these two are and subtract from 180 to get the missing angle. So that's going to give us 120 plus I don't know equals 180. Subtract 120 from both sides, and I don't know is going to leave me with 60 degrees. Same idea, 75 plus x plus 52 plus 67 plus x all should add up to 180 degrees. So now we've kind of gone to a math 1 equation, no longer just looking at that triangle. I could just combine like terms and solve. So x and x is 2x, 75 and 52, that's going to give us 127, and 67 is going to give us, had to grab the calculator, so those 3 angles add up to 194 equals 180. I'll subtract 194 from both sides. And I know a couple of you are starting to freak out a little bit because you know you're going to end up with a negative number here, negative 14. If I divide both sides by 2 to get x by itself, x is equal to negative 7. Well, remember, the angle measure is not negative 7, x is negative 7. So I could substitute this back in and still have positive angle measures, and they all add up to 180 degrees. We're going to prove the exterior angle theorem. The exterior angle theorem says that the measure of an exterior angle, so in this case angle 4, should be equal to the sum of the 2 interior angles that it doesn't touch. Well, we already do know that if PQR is a triangle, then angle 1 plus angle 2 plus angle 3 should add up to 180. So we're going to add that into our proof. Angle 1 plus angle 2 plus angle 3 equals 180. And that is the triangle angle sum theorem. So now, if I know that PRQ is a triangle, and I know that angle 1 plus angle 2 plus angle 3 adds up to 180, I also keep in mind that 3 and 4 are a linear pair. So my step 3 should be that angle 3 plus angle 4 equals 180. And then we'll just put linear pair, pairs are supplementary. Alright, so then that's going to allow me to be able to swap out 3 and 4 for 180. So step 4, I could substitute angle 1 plus angle 2 plus angle 3 equals angle 3 plus angle 4. And again, that's just substitution. So then, my last step, I have a 3 on both sides. So by subtraction, angle 1 plus angle 2 is equal to angle 4. And actually, I should write that the other way just to match my proof statement. Angle 4 is angle 1 plus angle 2. And again, that's by subtraction. So you can use that on these examples here. So for instance, this missing angle here and the two angles that it doesn't touch, 70 plus 50, should equal that missing angle. So 120 is that missing angle. Over here we kind of work a little bit backwards. 115 is the total of the two angles that it doesn't touch. So I'll just subtract 50 from both sides, and I get 65 is equal to that angle that I'm missing. Lastly, what we have here is, and I'll just give you the equation and let you solve this on your own, where 8 plus 6x is the total of 30 and 4x plus 2. You go ahead and solve that on your own, and you can find out what x is and then plug it back in if they want to know the angle measures. Okay, the isosceles triangle theorem. The isosceles triangle, remember, is a triangle that has at least two sides congruent. Well, the thing that we do want to also point out, because it's a triangle, there's angle relationships that are also present. So if it's an isosceles triangle, you also have a pair of angles that'll be congruent as well. And we say they're the angles that are opposite the two sides that are congruent. So for instance, this picture right here, if these are your two sides that are congruent, then the angles opposite would be these two angles. Well, the one side that's not congruent is called the base. So the angles on either side of the base are called base angles. And it's the base angles that are congruent. So if two sides of a triangle are congruent, then the angles opposite those angles are congruent. I'm sorry, that's the converse. Let me try that backwards. Oh, I messed that up on you. Let me try again. If two angles of a triangle are congruent, then the sides opposite. That's the converse. Remember, converse is when you switch the if and the then. So up here, if we switch the if and the then from that theorem, you would get that. I apologize. All right, and then here we go. Corollary, if a triangle is equilateral, then it is also isosceles. Keep in mind that an isosceles triangle definition uses that phrase, at least two sides congruent. So everything that's true about an isosceles triangle also works for an equilateral triangle. Keep in mind, again, the two sides that are congruent, if these are the ones that are congruent, this would be the base. And these would be the base angles. And these would be the legs because they're the two sides that are the same. Okay, the isosceles bisector theorem. Well, one of the things that's important about this is that the bisector of a vertex is the perpendicular bisector of the base. So because you have this symmetry in an isosceles triangle where this triangle and this triangle are the exact same, then all their matching parts are going to be the same. And the only way that these two angles can be the same and still form a linear pair is if they're both 90 degrees. And if these pieces match, then they're congruent. And so if these are congruent and that's a right angle, then this must be a perpendicular bisector. That's what the isosceles bisector theorem says. So given BAC, that's this whole angle here, is 70 degrees. Well, to get the individual angles, which have to be congruent because of the bisector idea, 70 divided by 2 is 35 degrees. So both of these angles would be 35 degrees. So angle ABC, we have to keep in mind that it's going to be 35 plus 90 plus whatever this is. So 35 plus 90 plus, I don't know, equals 180 degrees because it's a triangle. Combine like terms here, I get 125 plus I don't know equals 180. So then subtract 125 from both sides, and I get I don't know is equal to 55 degrees. So ABC is 55 degrees, which automatically means ACB is 55 degrees.